Hello and welcome to this online course on Advanced Process Dynamics. I am P. A. Deshpande from the Department of Chemical Engineering at IIT Kharagpur, and over the next 12 weeks we will engage ourselves in learning some new and advanced techniques with special relevance to process industries. We will also take examples from other domains like mechanical engineering, aerospace engineering, biotechnology, etc., but the prime focus will be on process engineering applications. So, before I start, let me give a brief overview of the course structure. Throughout this course, I will be accompanied by two of my graduate students, Abhishek and Maya Lakshmi. We will learn some advanced techniques. So, you will soon realize what do I mean by advanced when I go through the course contents. The prerequisite for the course is an elementary course on process dynamics and control. The general UG curriculum of chemical engineering introduces the students to process dynamics and control, but the course also comes with different names such as process instrumentation and control or control engineering. We will be starting every topic with a mathematical technique, and then subsequently we will be taking an example from process industry. So, therefore, it would be highly desirable if you have at least one of the courses on linear algebra or ordinary differential equation and transform calculation. So, we will meet every week for 5 times. Every lecture would be of 30 minutes duration, and we will complete the course for the next in the next 12 weeks. So, what we will do today is I will formally define the various terms which we will be using repeatedly in this course over the next 12 weeks in fact. So, let us start with the formal definition of process dynamics. The process dynamics involves the dynamics of change, and it can be analyzed in two different methods. It can be analyzed in state space domain, or it can be analyzed using transform domain. So, therefore, the first two parts of the course will involve the analysis of processes in state space domain, followed by analysis of processes in transform domain. Processes in industries are both linear as well as nonlinear, and we will do the analysis of processes in state space domain as well as in transform domain, which involve both linear as well as nonlinear processes. Further, especially with the introduction of computers for control of processes, several processes are no more in continuous domain, but they take place in discrete domain. So, we will also analyze how to do the analysis of process dynamics in discrete domain. So, these are the 4 different parts of the course that we would be covering in the next 12 weeks. So, let us start the course, and let us first ask ourselves the question that what is the meaning of dynamics. So, let us forget about process dynamics and let us first see what is the meaning of dynamics. I am confident that you have come across the word dynamics for the first time in your high school physics, where you learnt about statics and dynamics as 2 major branches of mechanics. I am also confident that you must have taken one or the other flavor of engineering mechanics courses in your engineering curriculum, and there also you must have been introduced to the concept of dynamics. In fact, I made this collage to remind yourselves of various problems or type of problems that you must have solved using one famous book by Beer and Johnston. And what do we actually understand by dynamics when we refer to the word dynamics in say pure physics or also engineering mechanics? So, the term dynamics refers to that branch of mechanics which deals with the motion of bodies under the action of forces. So, what is the keyword here? The keyword is that the motion of the bodies takes place and the coordinates of the bodies change with time. So, the keyword is change with time. Now, if you are a mechanical engineer, you would have used this concept by applying the concepts of dynamics to the motion of say vehicles, and that is what gives rise to the branch of what is called vehicle dynamics. Similarly, flight dynamics is studied by aerospace engineers, where they learn about how to make an aircraft airbound safely and also land it safely. And in both the cases, what happens is that the coordinates of the vehicle or the aircraft changes with time. Now, the question is, how can we perhaps use similar concepts or perhaps the same concepts in process engineering applications? The answer comes from the phenomenal work of mathematician Henry Poincaré, who developed the theory of dynamical systems, which was nothing but the analysis of ordinary differential equations. What Henry Poincaré showed is that even simplest of the ordinary differential equations can have very complex behavior as you change the state of the system, as you change the parameters of the system. And chemical engineers then realized that we can in fact use the concept of dynamical systems which exist in mathematics in case of process industries as well. So, what is the difference between dynamics in general and process dynamics? Process dynamics deals with the systems which undergo change with time. So, we can take several of such examples. One of the examples can be the staged operation of, for example, a distillation column. So, what you can see here is a distillation column with different number of trays, and let us consider 3 trays indexed as n plus 1, n and n minus 1. You must have been taught in your mass transfer or separation process courses that you can do a mole balance over one particular plate, and what you can see on the right hand side of this equation is the mole balance, and you used to equate it simply to 0 to determine how much of a particular component leaves one tray to go to the upper tray, or the liquid phase to go to the downward tray, and so on. But there was an inherent assumption that the process was taking place at steady state. But imagine that you have started your distillation column, and it is going to take some time for the system to reach the steady state, where changes do not take place with time, everything remains constant. Now, the question is, what happens during the time that you start your operation and then you go and reach the steady state? So, that is the transient dynamics that you need to capture, and that is given by this equation which you can see here on the screen. I have taken this example directly from the work of Akrivos and Amundsen, and the terms which you can see here have been used directly from the ones reported in the paper. So, in case you want to refer to the original work, you can actually look at this equation and refer to the original work. The equation is very simple, it is a simple transient mass balance equation. Okay. So, this is a dynamical system because the composition in each tray changes with time. So, change with time is important term here, and therefore, this is a dynamical system. Let us look at another example. So, imagine that you have a CSTR and you operate the CSTR under transient conditions. So, what is going to happen? Instead of one equation, you are going to now have 2 equations, because the concentration of the species is going to change with time. So, is the temperature of the species going to change with time. So, now you have 2 equations. In both the cases, what you see is that the equations involve change of concentration and change of temperature with time. So, therefore, although a traditional conventional CSTR is meant to be operated at steady state, but before the steady state is reached, the system experiences transients, and you can solve these model equations by analyzing the dynamics of the system, and you can come to know how quickly or how slowly does the system reach the steady state condition. Finally, we can take one more example and take the example of CSTRs in series. Okay. So, again you have transient operation of n cascade CSTRs with reversible series reactions. It is not very difficult to see from this schematic that you have a feed to this CSTR, you have a feed to the CSTR, and the reactant concentration with some initial concentration goes to the first CSTR, from the first one it moves to the second one, and so on. Okay. Again, during the steady state operation, you would expect the model equations to be independent of time, but when transient operation takes place, the concentrations of the species inside the CSTR changes with time, and therefore, you need to understand the dynamics of the system. So, therefore, we come across a lot of process engineering applications where the properties of or the variables associated with the system change, and the change happens in time. And dynamical systems or process dynamics is the study of such systems. So, let us define formally what is the meaning of dynamical systems. So, a dynamical system is defined as a system which has at least one variable which changes with time, which is a function of time. So, these are all the model equations which we saw in the past 3 cases, and what we see is that in all the 3 cases we have the system which changes with time. So, therefore, the case of a distillation column which is operating under transient conditions, or CSTRs in series, or a non-isothermal operation of a CSTR, all of these are the cases where the system changes with time, and therefore, you define such systems as dynamical systems. Now, what is the meaning of a dynamical variable? The dynamical variable is a variable which changes with time, and for such variables the time rate of change is described by the model equation. So, in these 4 equations you see that there are quantities which are highlighted in red. You have x of n, which is the molar composition over any tray of any component. Then you have C I of 1, which is the concentration of the ith component in a given reactor. Then for the case of CSTR, you have the composition as well as temperature which change with time. And in all of these cases, what you see is that you have identified a variable which changes with time, and such a variable is called the dynamical variable. Now, we can define traditionally the order of a system. In your undergrad process dynamics and control course, you must have studied the definition of an order of a system as the order of the ordinary differential equation that models the system. So, for example, if you take a manometer and do the dynamics of the motion of the liquid, the model equation comes from the Newton's second law, and since Newton's second law is second order, you say that the order of the system or the order of dynamics of liquid level in a manometer is 2. But now we have a problem. What you see here is that for the case of a CSTR, you have 2 equations, and each equation is a first order equation. And if such is the case that you have 2 first order ordinary differential equations, then what is the order of the system? So, now we define a new definition of the order of a system as the number of first order equations which are present in the system. So, order of a system will now be the number of first order ODEs that model the system. And is there a correspondence between the older definition and the new definition. Well, we can establish that. Let us consider a general second order ODE. So, the equation is A 2 d 2 x by dt squared plus A 1 dx by dt plus A 0 x is equal to b times some function of t. Okay. So, this is my general second order ODE, and let us say this ODE governs the system. So, the system is a second order system following our previous definition. So, now what I do is I define a new variable dx by dt is equal to y. Say this is the new variable. So, what I will do is I will substitute dx by dt is equal to y in equation 1. So, I get A 2 dy by dt plus A 1 y plus A 0 x is equal to b f of t. Okay. And this can be rearranged as dy by dt is equal to minus A 0 by A 2 x minus A 1 by A 2 y plus b by A 2 f of t. This is equation number 3. So, let us now analyze what we have done. I had previously one second order ODE which governed my system, and therefore, the system was second order, and I have converted it to two first order ODEs. So, this is the first order ODE and this is the second first order ODE, which means altogether I have two first order ODEs, which means that it is possible for me to convert any second order ODE to a set of two first order ODEs, and by induction I can say that I can convert any nth order ODE to n first order ODEs. So, therefore, our new definition that the order of a system is equal to the number of first order ODEs that model the system is in fact consistent with our previous definition. Okay. So, now let us take one more concept and define what a linear system is. Okay. So, we would be dealing with linear as well as non-linear systems. We need to first define what a linear system is. So, a linear system is defined as the one whose governing dynamical equations are linear. Now, this is a very recursive definition. Okay. We are defining a linear system as a system whose dynamical equations are linear. So, we need to properly define what is the meaning of linearity. How do you say that a system is that the governing equations themselves are linear. So, according to the principle of linearity, the first thing that you need to do is you need to identify the corresponding operator for your equation. So, our equations would be ordinary differential equations, and for every equation, for every ODE, you will need to determine the corresponding operator, and if the corresponding operator is linear, then your system is linear. Again, what is the meaning of the term that the corresponding operator is linear? Well, it needs to satisfy two conditions given by equations 5 and equation 6. Let us see what is the meaning of these two conditions. So, let us imagine that I have identified L hat as the operator. We will very quickly see how do I identify the operator, but at this point of time let us see that I have identified an operator and that operator lies in a linear vector space whose two elements u under bar and v under bar are known to me. So, u under bar and v under bar are the two elements of a linear vector space and L hat is defined in that linear vector space. Then the operator L hat is said to be linear if L operating on u plus v is equal to L operating on u plus L operating on v, and if alpha is any member of the field over which the vector space is defined, then L operating on alpha times u under bar should be equal to alpha times L operating on u under bar. Okay. So, let us quickly look into how we actually can establish this. Okay. So, let me say that I have a model equation which goes like this: d 2 x by d t squared plus a x is equal to 0. So, as I said, I need to identify the operator. Okay. So, let us see if I write this and you get convinced that this is the operator. L hat is d 2 by d t squared plus a. Okay. So, L is an operator, which means that I will have a quantity over which L would be operating. So, L operating on x means what? d 2 by d t squared plus a operating on x. And what is the meaning of operating on x? So, I have second order derivative here, which means I will have the second derivative of x with respect to time, plus a is simply a multiplication operator, which means I will have a x here, and my equation would be L hat x is equal to 0, right. So, I have done the first step, that is the identification of operator. So, let us see, I have d 2 x by d t squared plus a times x is equal to 0. Now, I need to verify whether the principles of linearity hold true. So, I say that let x 1 and x 2 be two solutions of equation 1. This is my equation 1. So, since I have a linear, if I have a linear system, the solutions would lie in the linear vector space. So, if the two solutions are any two solutions are x 1 and x 2, then I will have L operating on x 1 would be what? d 2 x 1 by d t squared plus a x 1, and L operating on x 2 would be d 2 x 2 by d t squared plus a x 2. Now, according to my first property, what I should do is I should operate L on x 1 plus x 2. So, what would this be? d 2 by d t squared plus a, and this must be operated on x 1 plus x 2. So, what I can do is I can write this L operating on x 1 plus x 2 would be what, d 2 x 1 by dt squared plus d 2 x 2 by dt squared plus a x 1 plus a x 2, which is nothing but d 2 x 1 by dt squared plus a x 1, and let me put a bracket here, plus d 2 x 2 by dt squared plus a x 2, which is nothing but L operating on x 1 plus L operating on x 2. So, my property of first property of linearity is indeed satisfied. Let us go and look into the second property. So, my equation is d 2 x by dt squared plus a x is equal to 0, and my operator is d 2 by dt squared plus a. According to my second property, if alpha is any member of the field over which the solution space is defined, then if I operate L of alpha times x 1, where x 1 is any solution, then what is going to happen is that I am going to write it as d 2 by dt squared times alpha x 1 plus a times alpha x 1. So, I can do a quick rearrangement. This would be alpha times d 2 x 1 by dt squared plus alpha times a x 1, which is nothing but alpha times d 2 x 1 by dt squared plus a x 1. And what is this equal to? This is equal to alpha times L of x 1. So, the second property is also satisfied, and I see that L operating on x 1 plus x 2 is equal to L operating on x 1 plus L operating on x 2, and L operating on alpha times x 1 is alpha times L operating on x 1. So, therefore, the operator here L corresponding to this equation in fact is a linear operator, and therefore, the equation also is a linear equation. So, now final question which arises in our mind is that how to analyze the dynamics or analyze the dynamical systems. As I made a mention in the during the beginning of the lecture, that there are basically two broader ways of analysis. One is called the state space domain analysis, the other one is called the transform domain analysis. So, when do we do state space domain analysis and when do we do transform domain analysis? Typically, most chemical plants these days operate 24/7 on a continuous mode of operation. So, if a plant operates for say 6 months continuously, and during that operation there would be small fluctuations in the process variables, and you will have control system implemented in it for maintaining the process variable. But then the question is that if you know that this is my say the level of temperature which I need, and the temperature falls down by 100 degree centigrade. So, I need to understand the dynamics of my system between two steady states. This is the first initial steady state which you want, the system has gone to the lower steady state, you probably would like it to come back to the original steady state, and so on and so forth. When you want to do the analysis of the system between the known steady states, then you do the analysis in transform domain, and this is typically what is taught in the undergrad curriculum. But then when you design a process, you would like to know what all can happen to my system. Will my system what is the maximum temperature, for example, which my system can reach? will my system be able to system parameters be able to afford that condition of temperature, pressure and so on. So, you are not merely focusing on the dynamics between two steady states, but you are trying to understand the dynamics between which is in every possible parameter space domain. In such a case, you use the state space domain analysis. We will begin our course by state space domain analysis. We will focus on the analysis of the systems using various concepts which arise during the state space domain analysis, and then during the later part of the course we will resort to the transform domain analysis. So, we will stop here today and we meet tomorrow with the new topic of analysis in state space domain. Thank you.